This fluid is being heated from below, like when the sun warms the ground at the bottom of the atmosphere. The moving fluid carries the heat upward from the ground. This is convection. The rising heated air gives a characteristic appearance to the clouds we call convective clouds. Speeding things up by time-lapse photography helps in seeing the action whole. In studying these clouds, meteorologists are finding the notion of bubbles to be a fruitful way of tackling the problem. We can visualize the bubbles as having buoyancy related to its temperature, size, and so forth. We see the bubble only where moisture condenses in it to form cloud. Here's a summer morning with the clouds just beginning to form. The bubbles aren't very big, and they top out only a mile or so above the ground. They show the air stirring like a boiling pot. If the stirring subsides, the clouds disappear. As the heating continues, the bubbles get bigger and rise higher. Notice the cauliflower-like tops and flat bases. The larger clouds are now from 1 to 3 miles tall. Each tower starts with a rush, reaches a certain height, then slows down and quickly collapses. But if a large cloud grows beyond some critical size, a new factor appears, the thunderhead. Heavy rain falls, mostly in a concentrated column. With the rain comes a host of new developments. There's a tremendous increase in cloud growth. Adjacent towers swell and merge rapidly with the main cloud, making it broader as well as higher. This cloud may be as much as 10 miles high from top to bottom and 20 miles across. The top of such a cloud changes from cauliflower to fibrous and starts to spread out like an anvil. Along with all this come organized, concentrated downdrafts of cold air, sometimes hail, lightning, tornadoes. We have watched clouds that started out as something like very simple bubbles. We've seen as they got bigger, they got extremely varied and complex. I'd like to understand better how these clouds work. Why do these clouds stay up? Why don't they sink down? Why do these clouds grow for a while and then collapse? Why do the large clouds grow still larger while smaller clouds nearby are disappearing? If we can discover some order in the apparent chaos that we've been watching, we can say we have won some understanding. In searching for order, I'm going to do what Einstein called a mental experiment. I'm going to disregard nearly all the aspects of the scene and consider only those aspects that I guess to be important. I'm going to simplify to the point where I can describe its form completely and specify its behavior exactly in an ordered way. Then, if I can manipulate this model in such a way that its behavior resembles the real clouds we were watching, then I can say I understand these clouds better. I've already hinted at the aspect of them that I'm going to select first. It is the notion of a cloud as a simple bubble swimming in a sea of air, rising unseen from the warm ground until condensation of moisture suddenly makes it visible. Even the moisture I can neglect at first. I choose for my mental experiment, then, a very simple universe, a sea of air, and a bubble also of air swimming in it. Here I have a studio-sized sea of water with a bubble swimming in it. If I make the bubble lighter by warming it with this lamp, it rises. It becomes buoyant. If I cool it with a lump of ice, buoyancy becomes negative, and it sinks. In either event, what I'm concerned about is the density difference between the bubble and the fluid in which it swims. To get at this difference, I'm going to spell out what governs the density of the air in the bubble and then the density of the air outside it, and so get an expression for the difference between them. For this, I don't need any new notions, just careful use of available knowledge. Specifically, I need the gas laws. There's air in this cylinder and a thermocouple to measure the temperature. If I warm it with the lamp, the pen moves to the right. There is also a pressure sensor, and if I increase the pressure, the pen moves downward. I arranged it that way because the pressure increases downward as one goes down into the bottom of the sea of air. Now, as you see, if I increase the pressure, the temperature also increases. I did work in compressing the air, and the energy I added to it appeared as heat. But now, to get back to my simple universe, I specify it as follows. I separate the bubble of air from the rest of the air by enclosing it in a limp skin, weightless, airtight, heat-tight. What matters about the bubble, namely its density, is completely determined by its temperature and its pressure. In this universe, I can disregard all other properties of the bubble. Since the skin is heat-tight, temperature outside has no effect on the density. But the limp skin exerts no pressure force. The pressure is always equal inside the bubble to that outside at the same level. I represent the external world, then, only as a pressure scale. Since I'm going to compare it later to the real world, I've made my pressure scale proportional to the mass of air above each point. So pressure increases downward just as it does in the real atmosphere. This is a proportional or logarithmic scale, and it's roughly proportional also to the height. The other thing is temperature. So I add a temperature scale, warm to the right, cold to the left. The state of the bubble at any instant is completely determined then by a point on this graph, its pressure and its temperature. If I cause the bubble to descend, the pressure increases and the work done raises the temperature. So it traces a path. This process is reversible. If I raise the bubble, the temperature and pressure decrease, and it retraces the path exactly. The line that the bubble traces on this diagram is called an adiabat, a word that means no heat flow and expresses the notion of a heat-tight skin that keeps heat from flowing into the bubble or out of it. The point corresponding to the bubble's state always follows an adiabat, up or down, as the bubble descends or rises. If I were to start with a series of bubbles at different temperatures, I would trace a series of adiabats and produce what is called an adiabatic diagram. This diagram shows for any starting pressure and temperature exactly how these two governors of the density will change as the bubble descends or rises. But my eye is on the difference between the bubble and the air it swims in, because that difference determines its buoyancy. So now I turn back to the rest of my universe, the air outside the bubble. I'm going to specify first that the temperature is the same at all altitudes and mark out a line of constant temperature on my adiabatic diagram. For my thought experiment, I enclose a piece of air here for my bubble. It is locked to this adiabat. If I raise it, it finds itself this much colder than the surrounding air at the same level, hence heavier. This is reversible. If I lower it, it is this much warmer than the surroundings. The situation in which displacement always gives rise to a force tending to restore the original state is a stable one, and this is a stable atmosphere. Next, I'm going to specify a different state for the part of my universe outside the bubble and repeat the experiment. Now the temperature is colder at the higher altitude. Again, I select a portion of this air and enclose it as my bubble. It is now locked to this adiabat. Now, if I raise it, it is this much warmer than its surroundings. And if I lower it, it is this much colder and heavier. The situation where displacement gives rise to a force that tends toward further displacement so that the former state is never recovered is an unstable one, and this is an unstable atmosphere. If I specify an atmosphere in which the temperature distribution is this way, then wherever I place the ball, the bubble is always at the same temperature as its surroundings, hence always at the same density, and it simply floats wherever it finds itself. This is neutral equilibrium, and this is a neutral atmosphere. I have specified a universe and spelled out the laws that govern within it. Now I'm going to try a mental experiment aimed at imitating the way convective clouds behave. I specify this temperature distribution copied from one measured early one sunny morning at Tampa. You notice the temperature decreases or lapses as one goes up. This gives the name of lapse rate to this way of picturing the atmosphere. And where the temperature increases, this is called an inversion. Now I take a bubble of air at the ground, warm it up to a mid-morning temperature, put it on the adiabatic track and let it go. It rises as long as it's warmer than its surroundings. When it reaches a point where its density is the same as the density around it, it comes to rest. If it overshoots a trifle, it falls back. This is my mental experiment. How does it compare with nature? This is a sunny day, and we can expect heated air to be rising in bubbles. But here is a cloud that doesn't fit the model. It looks as if some added buoyancy is being generated inside the cloud after it first forms that makes it shoot upward. If I can make a good guess as to why, I can improve my model. I note that this extra activity shows most in clouds where there's a lot of condensation going on. So I'll make a guess. I remember that it takes a lot of heat to turn water to steam in a furnace, and the steam gives up this heat again when it condenses back to water in a radiator. Was that cloud steam heated? Is that why it was kicking up? If so, I'd better include water vapor in my bubble model. Again, I use available knowledge to give exact form to this idea. There are 2 points to cover. One is the temperature at which water vapor begins to condense, and the other is the amount of heat it releases in condensing. About 1% of the atmosphere in this studio is composed of water vapor, and it exerts a like proportion of the atmospheric pressure here. If I cool the water in this beaker, at some point, water vapor will begin to condense on the glass. For every value of water vapor density in the atmosphere around, there is a particular value of this dew point temperature, and any further cooling causes more water to condense. Here, let me show you. We have a chamber here divided into 2 sides. On the left-hand side, it has been moistened by putting in a warm, wet towel. The right-hand side is relatively dry. I'm going to increase the pressure by pressing down on the top and cause it to warm up a trifle, and in the left side a little more water vapor evaporates. Now I let the pressure go, and it expands and cools. The moment the air cools below its dew point, cloud droplets form. Next time there are bits of fair weather cloud near the sun, look at them through dark glasses, and you will see interference colors like these. I said this water vapor gives up a lot of heat in condensing to water drops. Let's see how effective this steam heating is. Here we have an electric fry pan with 2 chambers set on top of it. The one on the left has a pan of boiling water in the bottom, and it's filled with steam. The one on the right is dry. The temperature in each of them is just the temperature of boiling water, 100 degrees centigrade. Now I'm going to put a lump of ice into each chamber. And wipe the window so you can see what's going on. In the right-hand side, air is giving up 24 calories per gram as it cools from 100 degrees to 0. But on the left-hand side in the steam is giving up 580 calories per gram just condensing to water, and another 100 calories per gram cooling down to the temperature of the ice. Now back to the adiabatic diagram. I take a bubble of air at point P, T, and spray some water into it. The heat to evaporate the water can't come through the heat-tight skin of the bubble, so it has to come from the air inside, and it cools. I keep adding water until it won't evaporate anymore, until it is saturated just like the air inside that cloud chamber. If I now cause the air to descend, nothing new happens. It follows an adiabatic curve just as before. But if I cause the air to rise, then some of the water condenses, and its heat is added back into the air, so that we follow a curve that lies on the warm side of the old one. If I keep on lifting this until all the water is condensed, drain it out, and bring the bubble back down the dry adiabat, I come back exactly where I started. Now I have all the laws I need for a new try at imitating nature. So back to that sunny morning. This time I give the bubble a shot of water and then warm it up against the sun-warmed ground until all the water is evaporated. Now it carries with it also the extra heat that it took to evaporate the water, even though its temperature is just the same as before. Let it go, and it rises. Here its buoyancy is almost gone. It's just about the same temperature as surroundings. But here it cools to the dew point and condensation begins, returning heat to the air in the bubble. It switches paths, and now it stays to the right of the lapse rate and gains buoyancy, so it gets a new upward kick after condensation begins. There, our model is one notch better at imitating nature. But there's still a glaring shortcoming. Only the very largest clouds grow as high as the model predicts, and the smaller the clouds are, the more they fall short. I have to make another guess, this time having to do with the size of a cloud, I think. Now, I know that small things have much more surface area in proportion to their insides than large things. And the real bubble obviously does not have an airtight skin. So what if I treat the surface skin of the bubble as a mixing region? Two deductions follow if the bubble picks up air from its surroundings and carries it along. There is drag, and there is dilution. Now back to the water tank. I'm going to make some small bubbles with a high proportion of surface area to volume. And then make a larger bubble. Notice that drag holds back the small bubbles much more than it does the large one. Now regarding dilution, in this other tank over here, I'll make a small cloud and then a larger one. As they sort of turn inside out, outside stuff gets into the core of the small cloud much more directly than it does into the core of the big one. And you'll notice too that the big cloud moves much farther in making one inside-out turn than the small one does. So the small cloud is really at a very severe disadvantage. And so we have a model that really does a very decent job of predicting the growth of convective clouds. from a given lapse rate, computing stepwise the buoyant rise of the bubble as condensation of water takes place in it, as drag and mixing work on it. Researchers are following up other guesses as well. Guesses about rain, about shearing winds, about the effects of neighboring clouds on each other. And these studies are leading to a better understanding of the role of convective clouds in transporting heat in the atmosphere, in making its energy available to drive storms. And what we can understand, we will one day control.